All right, today's lesson is talking about 2.1 and specifically about the vertex form of a quadratic function. So this lesson is going to kind of go through what is a quadratic function. There's different ways to write a quadratic function. There's different forms to put it in, and every form kind of tells you different information. So this is one of them. I think we're going to look at a total of 3 of them across this unit. So the vertex form is basically telling you what the vertex is. So if I have a quadratic that's in vertex form, I'll be able to look at that function and it'll tell me exactly what the vertex of that quadratic is. I won't have to do any calculations. I'll just be able to look at it and interpret that information. All right, so down at the bottom of page 73, that's where we're at, pages 73 through 79. It just kind of goes into what is a quadratic function. So a quadratic function is an equation that can be written in the form f of x equals ax squared plus bx plus c, but the caveat is a can't equal 0. So basically you have to have an x squared term in that function. So just a quick few examples. If I have something like y equals 3x squared, that's a quadratic function, right? It's got an x squared term, and my a value is 3. You could have something like this, y equals x squared minus 4, right? Again, the caveat is this x squared term. You have to have that there. So if I have something like this, y equals 2x squared minus 3x plus 7, right? That's a quadratic function. But something like this, y equals 0x squared plus 5x. That is not a quadratic function, because technically what that is y equals 5x. If I have 0x squareds, what's happening here is I'm multiplying x squared by 0. So I don't have any. So really what I have is just y equals 5x, which is a linear function. So in order for something to be a quadratic function, it has to have an x squared term, and a cannot be 0. All quadratic functions are transformations of the parent function defined by f of x equals x squared. So here's an example of f of x equals x squared. This thing isn't shifted left, right. It's not stretched or compressed. It's not moved up or down. That's just the parent function. But then we can move it around. We can adjust it to create a child function, right? That's where you'll have different numbers in an equation. So something like a child function would be something like this. Y equals 3x squared plus 4x minus 2, right? We could put that equation in vertex form, and it would tell us if there's a stretch or compress. It would tell us if we shifted left or right, up or down, if we reflected, all that kind of information. So the graph of a quadratic function is called a parabola. So this shape that x squared, that quadratic created, is called a parabola. So it kind of looks like a happy face or a frowny face. The vertex form of a quadratic function is just like this. So this is just the algebraic definition of a vertex form. So f of x equals a times x minus h squared plus k. So let me kind of break down what that means. Y equals a x minus h squared plus k. All right. So this a factor, right, that thing's being multiplied by x minus h squared. If a is greater than 1, that's going to stretch out your function. And we'll see some examples of that here in a little bit. So it's basically going to take this function that normally looks like this, and it's going to stretch it out and make it a lot more kind of, it's going to vertically stretch it out. Take the top and kind of stretch it, take the bottom and stretch it, and makes it more narrow. If a is between 0 and 1, then it's going to compress it. So it's basically going to start from the top. So here's our x squared. This is a stretch. So a compress would look something like that. So a compression basically flattens it out. Then I have h. So h is going to move me left or right. But the caveat with h was it always moves you in the opposite direction. Remember, we talked about back in some lesson in chapter 1, the formula is x minus h. Another way you could say that is the opposite of h. So because the formula actually has a minus sign or a negative sign in it, it's always going to move you in the opposite direction. So something like this, y equals, I don't know, x plus 7 squared minus 2. That says plus 7, which might make you think, oh, it's just going to move right 7 because that's the positive direction. But the formula is minus h, the opposite of h. So the opposite of positive 7 is negative 7. So this function would actually move left 7. The other thing I want to say about a is if a is negative, if that a value is negative, like a -2 or a -1/2, it's going to reflect you. These should sound familiar. We talked about transformations back in chapter 1. So if this is all old news, that's good. So this a value is going to reflect you across that x-axis. So it's going to basically flip you upside down. So if this is an example of x squared, right, is that graph right there, y equals negative x squared would basically be the same graph, but just flipped upside down. Okay. And then the last thing is k. My k value is going to tell me to go up or down. And you do exactly what it says because it says plus k, so I'm going to do exactly what k tells me to do. If my example over here is -2, I'm going to go down 2 because down is the negative direction. All right, example 1, transform a quadratic function. How are transformations of the graph of f of x equals x squared related to an equation representing another quadratic function? Vertex form shows 3 different ways in which a graph of the function f of x equals x squared may be transformed. So we talked about transformations back in chapter 1, that there was way more than 3 different transformations, right? We talked about there being a b value here, right in front of x, and that would be like a horizontal reflection, right? It would reflect you across the y-axis or stretch or compress you horizontally, not vertically. But they're focusing in this lesson on just these 3 specific transformations, A, H, and K. You can see my printer ink is getting a little bit low. So that's what we're focusing on, is just those 3 transformations in this lesson. So the value of A determines the direction the parabola opens up or down. Remember, if that's just a positive value, it's going to open up. It's going to be happy, right? Positive people are happy. If that's a negative value, that's going to open down because it kind of looks like a frowny face, right? So if that's positive, it opens up. If it's negative, it opens down. Don't forget, we just talked about, if that a value is greater than 1, it's going to stretch that function. So all of those y values are going to get taller and taller and taller. If that a value is between 0 and 1, it's going to compress it. It's going to flatten it out like a pancake. Our h value, that moves you left or right, but again in the opposite direction. And the k value moves you up or down in the actual direction it's telling you to. So in these examples, example A, looks like it's giving you 2 of the 3 transformations they want you to focus on. Technically, they're saying A, H, and K, but there's really not only 2 things happening here, there's 3. Let me explain it. So their A value is -1/2, which is basically 2 different transformations in one. So the negative is telling me to reflect it. So you could see this is my basic parabola, right? And then they reflected it, so it flipped upside down. And that same A value is also compressing this function by 1/2. So let me emphasize what that's talking about here. In our basic parabola, y equals x squared, that's this one right here. Notice that my values for this parabola, if I go over 1 from the vertex, I go up 1. Okay, over 1, up 1. And the reason why is because I'm just plugging in x is 1, and I'm doing the math. So if x is 1, 1 squared is just 1. So if x is 1, y is 1. Over 1, up 1. Let's look at this point right here. Let's do this one, because that looks like that parabola passes through the grid lines perfectly right there. They're saying that a point on this parabola is 2, 4. And that makes sense. We can verify that, because if I take my parabola, x squared, and I plug in 2, right, y equals 2 squared. I plugged in x equals 2. I do the math. 2 squared is 4. That works. So that should be true. We'll take a look at my translated graph here, my transformation. Do I still go over 1, up 1? Well, it's reflected, so I should go over 1, down 1, which is right here, right? Over 1 from the vertex, down 1. I'm not hitting my graph. So I know that this new graph, this new transformation, had a stretch or compress, because I'm not hitting that original point 1, 1. So let's take a look. From the vertex, it looks like if I go over 1, I'm only going down about half that amount. Same thing with this other point, 2, 4, right? Normally, if I go over 2, I'll go up 4. Let's check it. From the vertex, if I go over 2, and you can go either direction, it doesn't matter if you go left or right. If I go over 2, I should go down 4. 1, 2, 3, 4. But obviously my graph's not there, right? So how much do I actually go down? Over 2, down 1, 2. So instead of going over 2, down 4, I'm only going over 2, down 2. I'm only going down half that amount. So that tells me that I'm compressing by a half. So I reflected. You could visually see that. It was a happy face. Now it's a frowny face. We just talked about the stretch or compress. This is compressed by a half. And then this says x plus 2. So you might think, oh, it should have gone right 2. But remember, we're always going in the opposite direction. So we're going to go left 2. So every point on this original parabola here, every single point shifted left 2. Typically, you'll just talk about the vertex, right? The vertex was at 0, 0. Now it's at negative 2, 0, because everything shifted left 2. So same thing here. This looks like it's got two different transformations. A is 2, H is 1. So A is 2, H is 1. So this says x minus 1. So remember, you're always going to go in the opposite direction. So instead of thinking of going left 1, because that's the negative direction, you're going to go in the opposite. So I went right 1. Okay. I think there should be something else here now that I look at my graph. It looks like that says negative 3. So now I do have 3 transformations. K equals negative 3. So that tells me to go right 1. So I went and moved right 1. That negative 3 tells me to go down 3. So I went down 1, 2, 3. And there's my new vertex. So I went right 1, down 3. But remember, a basic parabola, a parent graph of a parabola, is always going to go right 1, up 1. Because 1 squared is 1. It'll go right 2, up 4. Because 2 squared is 4. Whatever you plug in and you square it, you should go up or down that far. So let's see what happens. In our new parabola, it looks like we go right 1, up, not 1, right? There's nothing there. So how far do we have to go up? It goes right 1, up 1, 2. So I went up twice the normal amount. So I know this has to have a stretch of 2. It went up twice the normal amount. Same thing, let's see if we could fit this on the graph. If we go over 2, we typically go up 4. 1, 2, 3, 4. But obviously that's not there, right? So we go over 2, up 1, 2, 3, 4, 5, 6, 7. You can see it's crossing right there, 8. So normally we should go over 2, up 4, but now we're going over 2, up 8. So we're going up twice that amount. So that a value, that's always going to affect your y values. It's basically taking every y value from your graph and it's multiplying it by that amount. So it took every y value and it multiplied it by a half. It took every y value and multiplied it by 2. All right, here's some examples down here you can try if you'd like. Let's look at example 2 here. Determine key features of a quadratic function. Tons of key features. I think they're just focusing on a couple here, right? You could talk about domain, range, positive, negative, increasing, decreasing. There's a lot of information, and I wish they told you specifically what they wanted you to find. But if you look at the example, they just point out a couple of things. So they're saying, let me fill this in, 4, it's a 3, that's a 2. So given this graph, 2 times x minus 3 squared plus 4, what are those different pieces of information telling you? Well, that 2, that's my a value. That's a positive 2, so I know it's going to be a happy face. So you can see that that's a happy face. That 2 tells me I'm going to stretch by a factor of 2. So all of my y values are going to go up. They're going to be multiplied twice the normal amount. So here's the normal amount. Normally, I would go from my vertex, I would go over 1, up 1. Over 2, up 4. 1, 2, 3, 4, right? So that kind of looks like my parent graph there, okay? But you can see what they're doing here. They're going over 1, up 1, 2. Over 2, up, that would be 8, right? Because they're multiplying all those y values by 2. So it's been stretched by a factor of 2. Not reflected, because otherwise it would have to be negative. X minus 3 squared, so that's telling you to go right 3. Remember, always go in the opposite direction. That says x minus 3. The opposite of negative 3 is positive 3. So you can see they moved their vertex from 0, 0. They moved it to x equals 3. And then their k value is 4, so they went 3, 4. So they went up 4. Example 3, write an equation of a parabola. So let's take a look at what they're asking. What is the equation of a quadratic function with vertex -2, 3, and the y-intercept of -1? So now they're just giving you some of the information, and they're going to expect you to kind of create the function. And it looks like they're giving you the graph there too. So just by these 2 points, though, because technically this is a point, right? -2, 3. This is a point. If it's a y-intercept, we know that that point is 0, -1. So with those 2 points, we can find all the information we need. So what you have to remember is that we have a generic function for a quadratic. We know that generic function looks something like this. Y equals a, x minus h squared plus k. So what they're doing is they're giving you 2 very specific points. They're giving you all of the missing information, your h and k, because that's your vertex, right? This is h, this is k. Your y-intercept, so this is giving you an x, it's giving you a y. The only piece of information that's missing here is that a value. So what we're essentially going to do is take that generic function, plug in those missing pieces of information, and then we're going to solve for a. So let's go ahead and do that. So here's my generic function, y equals a x minus h squared plus k. They're telling us that our vertex is -2, 3. So h is -2, k is 3. How do I want to do this? So I'm just going to kind of replace everything here. I'll replace h with -2. I'll replace k with 3. And then they're giving us the y-intercept. So that's an x and a y. So I'm going to replace x with 0. I'm going to replace y with -1. And now you'll see we've got an equation with only one piece of missing information. So now it goes back to PEMDAS. It goes back to just solving an equation for A. So be careful here when you're plugging this information in. Notice I actually put -2 inside a set of parentheses because it's x minus h. H, they're telling you, is -2. So it should be 0 minus -2. So be careful when you're plugging this information in. So if we start solving this, inside the parentheses, 0 minus -2 is 2. The next thing in PEMDAS is exponents. So I'm going to go ahead and multiply those, or 2 squared is 4. I'm going to rewrite this just because I like my coefficients to be up front. I'm not doing anything here. I'm just rewriting it. And now I can just solve for A. So based off of this given information for this quadratic, I know that my A value is -1. So now I've got all my pieces of information that was missing. I've got my A value, I've got my H, and I've got my K. So here we go. It's always y equals. You could also write f of x equals. It doesn't matter. Those two things are the exact same thing. I just write y because it's less stuff to write. We know my A value is -1, so you could write it like this, or you could just write it like that. It's up to you. It's x minus h squared, so it's going to be parentheses x h. What was that again? So h was -2. So you could write that as x minus -2. I'm just going to kind of simplify it. So when I subtract a negative, it's the same thing as adding. Again, if you want to write it like this, feel free to, right? This is just a little bit more simple. And then K, they're telling you that's 3, so I'll write +3. So this would be my final answer. You really should, once you plug that in, if you decide to do that in a step, you should simplify that. You should rewrite this as -x plus 2 squared plus 3, because that's what you'll see as options on the test. I'm not going to give you an option that looks like that. It'll be simplified. All right, so you could walk yourself through all that information. It basically does the same thing that I just explained to you. Plugs in the missing information, solve for A, substitute everything back in, and then it gives you that function right there. Example 4, write an equation of a parabola given the graph. Now instead of giving you missing pieces of information, they're actually going to give you a graph, and you're going to have to pull the information from this graph. So you're going to find the same information that they gave you in example 3. You're going to find the vertex, and you're going to find a point on that graph. It doesn't matter which point you choose. It looks like they end up choosing 0, 4. So it looks like they chose the y-intercept. If you want to choose the vertex or some other point that's on this parabola, every single point works. It doesn't matter. You could choose any point on the parabola. So let's read through this. The height of a thrown ball. So typically you'll hear these story problems like, somebody shoots a bullet, or somebody shoots a rocket, or somebody throws a free throw in basketball, or throws a football, or something like that, right? These things that behave like a parabola, things that go up and then things that come down. So those are the typical type of story problems. Thrown ball is a quadratic function of the time that it's been in the air. The graph of the quadratic function is the parabolic path of the ball. The vertex of the graph is at 120, so super important. This thing only has one vertex, so vertex is at 1, 20. And the path of the ball includes the point 0,4. So they're actually giving you a point that they want you to use. Again, I guess you couldn't use the vertex, so I misspoke earlier, because you're actually using that as one of the 2 points. So you couldn't use the vertex twice. But you could use 0,4. It looks like this thing passes right there. So you could also use, 1.4 comma 16, which, now you're dealing with decimals, so that might suck. If they give you a specific point, you got to use that. Just, you might as well. Plus 0.4 is going to be way better than 1.4 comma 16. With that information, go ahead and create the function. They want you write the quadratic equation in vertex form and in the form standard form. That's what they call that, standard form. So if that's in vertex form, we're going to do the same thing that we just did. We're going to create the vertex form. So y equals ax minus h squared plus k. Our vertex is 120, so that's my h value, that's my k value. So it's going to be h is 1, k is 20. And then they're giving you the second point because that gives you an x and a y. So x is 0, y is 4. So just like we did in the last example, use PEMDAS, order of operations, right? Solve this. So that'll give me 4 equals a. 0 minus 1 is -1. -1 squared is 1. I think I'll go ahead and subtract 20 from both sides, and I get -16 equals a. All right. So if I created this vertex form of this function, it would be y equals, again, or f of x equals, it doesn't matter, whatever you want to use. My a value is -16. H is x is 1, so it would be x minus 1 squared. K is 20, so plus 20. So there is my vertex form. I can just look at this function and pull out information. Oh, my vertex is at 1 comma 20. My a value is -16, so I know it's reflected. It's going to be a frowny face, and it's going to be stretched by a factor of 16. So instead of going over 1 down 1, you're going to go over 1 down 16 times that amount. Okay. And then they want it in standard form as well. Ax squared plus bx plus c. They call that standard form. So the only way to do that is to just basically use PEMDAS, order of operations. Multiply this all out, and then put it in standard form. So the first step would be PEMDAS, parentheses. There's nothing inside the parentheses I can simplify. X minus 1, they're not like terms. I can't simplify it. So then exponents. So x minus 1 squared. Notice just the x minus 1 is being squared. You're not squaring the -16. Okay? So x minus 1 squared. Some people, just a quick review, if you're squaring a binomial like that, a lot of people have done this box method where they'll set up a box and they'll multiply each row and each column. So row x times -1, -1 times x, -1 times -1, and then they just combine like terms. So there's only one x squared, -x minus x, that's -2x, and then there's just a +1 down there. That's typical. A lot of people use that box method. Some people will FOIL it out, so they'll do x minus 1 squared is the same thing as x minus 1 times x minus 1. And then they FOIL it. So first times first, outer times outer, inner times inner, last times last. Okay, lots of different ways you can multiply out a binomial. Typically, those are the two most popular. Now I've got the -16 that I can distribute throughout that set of parentheses. So it's going to be y equals -16x squared plus 32x minus 16. Don't forget about that plus 20 at the end. Now I can combine like terms. So my final answer would be y equals -16x squared plus 32x plus 4. So there is my vertex form. There is my standard form. So vertex form, basically plug in your vertex. plug in your x and y that they give you, that extra point, solve for a, and then you can plug everything into the generic function. And then to get standard form, you just multiply everything out. Simplify it. Let's see. And that's exactly what they're doing down here. They're just showing you all those steps and explaining that. So the top is just more of example 4. Let's take a look at example 5. Write an equation of a transformed function. So the function g, which is this one that's kind of up and to the left a little bit, is a translation of the parent function f. So this is just f. It's just basic x squared, right? Nothing's been added, subtracted, multiplied, stretched, compressed, reflected, nothing. So g, that's when you start moving things around and stretching things and reflecting things, okay? Write the quadratic equation in Vertex and in standard, so they want you to do both, so we'll have to figure that out. So Vertex, I would go Vertex first. If this is my parent function, let's double check and make sure kind of from start to finish. Let's look at our a value, our h value, and then our k value. So a, that's going to tell you 3 possible things, right? It's going to tell you if it's reflected, which it's not. The f function is a parabola that's facing up. It's a happy face. G is also a happy face, right? They're still both facing up. So we know G is positive. I should really write this like this. G of x, f of x, just to be like correct. So let me write this down here. G of x equals, again, it's still facing up. It's not reflected. What about stretched or compressed? Well, let's take a look. Here's the basic function. So I go over 1, up 1, right? Because 1 squared is 1. All I did was plug in 1 and squared it to get how far I go up. Let's check this one. Let's do another one. Over 2, up 4. 1, 2, 3, 4. Again, all I'm doing is this. I'm plugging in 2, and 2 squared is 4. So this is how far I'm going left or right. Once I square it, that tells me how far I'm going up or down. So let's check our transformed function. Start at the vertex, over 1, up 1. Okay, so far so good. Let's check another point. Over 2, I should go up 4. 1, 2, 3, 4. Yep. So I'm pretty sure this is not stretched or compressed. So our a value is just 1. So I'll start off with my parentheses. It looks like our vertex did move. You could pick any point and see where that point moved to, but typically people look at the vertex. That's where I'm going to judge. Where did the vertex go from and to? It looks like it went left 1, up 3. So every point on this parabola, on this f parabola, every single point moved left 1 and up 3. You could see this point right here, right? That moved left 1, up 3. This point moved left 1, up 3. So if I want to go left 1, remember, it always has to go the opposite direction. So I don't want to write x minus 1 because that would tell me to go right 1, right? I always want to go in the opposite direction. So if I want to tell my parabola to move left 1, left is negative, so I'm going to write the opposite, positive 1. And then it went up 3, so it's up 3. So there's the vertex form. The standard form, again, we just have to multiply this out. So x plus 1 squared, that's just going to be x squared plus 2x plus 1. Again, just like we talked about on that last example, use the box method, FOIL it, whatever you want to multiply out a binomial. If you don't remember that, just go ahead and look up a video on multiplying binomials. You'll see a bunch of different methods. There's lots of ways you can do that. Then our last step, combine like terms. Looks like I got a 1 and a 3. So if I combine like terms, I'll get x squared plus 2x plus 4. So there's my vertex form, and there's my standard form. All right, then at the top of page 77, that's our concept summary. So this just kind of emphasizes everything that you talked about in this lesson. what a quadratic function is, how you can represent it, different things that happen once you add transformations into it. So this is a parent function, just x squared. But once I add a, h, and k, it's going to move things around. It's going to stretch, compress, reflect, all that kind of stuff. So that's just kind of summarizing that information. And then this is just telling you, here's an example of a quadratic, and here's all the information you could pull from it. So you could find the vertex, h and k. Remember, h is always going to be the opposite. So it says x plus 2. So I know my vertex is going to be negative 2, comma 3. Axis of symmetry, that's something that I didn't see. Maybe I missed it when I was going through things. But an axis of symmetry basically says that any quadratic, doesn't matter if it's stretched, compressed, reflected, doesn't matter what it looks like. So any quadratic is always going to have an axis of symmetry. So let's say this thing moved around and it moved up here. Okay. And let's say that it moved over to, 4. Okay. So this parabola moved right 4 up. It doesn't matter. We'll call that 3. Let's say it was stretched by a factor of, 2 or something like that. Every parabola is going to have that line of symmetry that when you draw a line down the middle of it like that, basically the right side maps to the left side. So let's say that this point right here is 5, 4. 5, 4. Okay. Well, I know this point is going to map to this point perfectly if this point is only 1 unit to the right and 1 unit up. Then this point right here is going to be 1 unit to the left and 1 unit up. So every point on this right side will be the same distance away from this axis of symmetry as all these points on the left. They're always the same distance from each other. So that point and that point, if this point is 3 units to the right, this point will be 3 units to the left. Same height, just the distance is the same. So that's what they call the axis of symmetry. If it opens upward or downwards, remember that's your A value. If it's positive, it's happy, smiling. If it's negative, it's a frowny face, so it's going to be opening down. The vertex will also tell you maximum or minimums. So you could see right here with this parabola, it's got a minimum because this parabola comes down and it bounces off of that point and goes back up. So it'll never drop below that point, y equals 0. But this other parabola, the g of x, you could see that it comes up and then it bounces off of this point right here. So it's got a maximum. That's the maximum height it'll reach at y equals 3. So maximum, minimums. Domain and range, something we talked about. How wide can a function get? How tall can a function get? All right. So I think it is time to start going through our examples. All right, so the practice section. Describe the transformations of the parent function, f of x equals x squared. Then graph the transformed function. Woo. So you could have graph paper. You could just sketch it. If you want to open up Desmos, that's what I would recommend. And that way you could just graph it just to see visually what's happening here. So describe the transformation. There's no a value, so it's not stretched, compressed, or reflected. It looks like it moved right 1, because remember, it's always the opposite direction. So right 1 and up 3. So I'm going to go ahead and do this for one of these, or maybe a couple. So this is number 16. If this was my parabola right here, and I'm just sketching this, I'm not going to actually take the time to plot every point. And we'll call this our coordinate system. It's going to move the vertex right 1 and up 3. So right 1, up 3. 1, 2, 3. So now it's going to look like that. Nothing got stretched, nothing got compressed. I mean, of course, if I was doing this perfectly, all of these points would still match. It would look identical. The only thing that moved was right 1 and up 3. Every point moved right 1 and up 3. 17, again, no a value. It looks like this is moving left 1 and down 3. So if I were going to draw that based off of this parent function, this one where the vertex is at the center, it would move left 1 and down 3. So left 1, down 1, 2, 3. And it would look something like that. So imagine the parabola looking exactly the same. The only thing that moved were all the points on the parabola. 18 is interesting because 18 doesn't look like it's in vertex form, but technically it is. I can rewrite number 18 as g of x equals 2 times x minus 0 or plus 0. It doesn't matter what you want to write there. Squared plus 0. So technically those two things are exactly the same. It is in vertex form. It's just they're not including all the zeros that are in there. So the only thing that with number 18 that they're doing is stretching it by a factor of 2. So if I have my parabola, there's my parent function. If I stretch all of those y values by a factor of 2, what's happening is every single y value on that parabola is being multiplied by 2. So instead of going over 1 up 1, if my graph was perfect, I would go over 1 up 2. I'm going up twice that amount, right? So that a value is just multiplying all of your heights, all your y values. X's don't change. You still go over 1. You still go over 2. You still go over 3. But this would tell you I'm going to go up twice the normal amount. 19, this looks like it's going to be reflected. The vertex is going to be at 1, 7, so I'm moving right 1 and up 7. And I'm going to go ahead and sketch this one out for you real quick, just because that reflection is something different. So if this was my parent function, my vertex, again, it would tell me to move right 1 and up 7. So we're going to call this right 1, and we're going to say that that's up 7. So there's my new vertex. Again, the scale's not perfect, but you can get the idea. I went right 1 and up 7, but then I'm reflected. So now instead of going over 1 up 1, I'm going to go over 1 down 1. Instead of going over 2 up 4, because 2 squared is 4, I'm going to go over 2 down 4. Right? So it's just going to be flipped upside down. So same parabola, I just took it and I moved it right 1 up 7, and then I just flipped it upside down. Number 20, this has got some more transformations, so it's definitely reflected. It's stretched by a factor of 2. I'm shifted left 1 and up 1. So this has basically all 4 things. Reflected, stretched by a factor of 2, shifted left 1, shifted up 1. And then 21, this is 1/2. So now I'm compressed by a factor of 1/2. So this is going to get flatter. I'm going to shift right 2 and up 3. So right 2 and up 3.